Yep, that should be fine. Okay. So just for reference, this exam was on the difficult end of the spectrum for exam 2s. And in particular, this question wasn't answered very well. Not all the parts of this question weren't answered well, but there were a lot of parts of the questions where only 1 or 2% got full marks, as in 1 or 2% of the students got full marks. And just another note that this question was 18 marks in total out of 80. So that's roughly 25% of the exam. So as in terms of length. So this is like a really hard question. You would have to spend a lot of time on it. And that's why this exam was difficult, because you had this question along with other more difficult short answer questions. So overall, it makes for a good challenge, and it makes for good preparation for your integration SAC that should be coming up soon. And just to emphasize, the integration SAC is not limited just to integration. There's other topics in there, and assume that everything else that you've learned from the start of the year up until now is assumed knowledge. In particular, differentiation. We actually get, from a couple of my private students, I get questions all the time. Is differentiation going to be asked? Well, most likely yes, because differentiation is highly related to integration, because they're just opposites of each other. So it's really important that we learn, or that we perfect differentiation as well as integration, as well as all the other things that we've learned up until this point in time. And you can see the first question, part A, it already has transformations. So that's just a big indicator that exams don't keep questions strictly to one topic. They always mix it. And that's the same for SACs. But when we're going through today's question, I'll try and show you how to do it. But I think just as importantly, I'm going to show you how to structure your working out, and I guess give any tips, marking distributions, and things like that. So just little things that your teacher might not go over in class. Obviously, your teacher should go over the theory, but also how to answer questions, how to use your calculator, how much working out is required. I think those things are also really important as well. So let's start reading this question. Luckily, there's not too much information behind this question. It just gives us a function, f of x is equal to 2 to the power of x plus 1 minus 2, and then give us a graph as well. So as soon as I see this question, well, presumably you would have read it in reading time, but as soon as I see this question, I think, okay, there's a few of these parts of this question that require f of x. You can see we go up to part D, and we need f of x in all of them. So the first thing that comes to mind is that I should define the function of my calculator. Now, this isn't necessary, but I think it's really good thing to do, just because you use the same function multiple times. It saves you so much time in the long run. So quickly just define the function. It's a very similar command on the TI. I just write down my function, and then I go interactive define, and then the default one is f. And then that defines my function. So that's done. And now whenever I do calculations, I could just use reference f of x rather than typing out my whole equation again and again. Now, part A says we have a transformation, and it gives us the transformation notation that defines this t. And it says it maps y equals 2x onto our graph of f, which is 2 to the power of x plus 1 minus 2. Now, might seem a bit unclear from the words. What I like to do is write this out as just transformation notation, as in what's my pre-image or the function before I translate, and what's post-image or post-transformations. So it becomes this. So 2 to the power of x becomes 2 to the power of x plus 1 minus 2. Now, a common mistake that people make with these questions is that they mix up the transformation order. You have to be really clear, or you have to interpret the question properly. And you have to see which graph goes to the other one. So for example, this one says it maps the graph of y equals 2 to the power of x onto the graph of f. So we know it goes from this to f of x. But just keep in mind, it could be the other way around. It just depends on how the question is worded. So this one's pretty clear. Sometimes they might use the term image and pre-image. So pre-image, pre implies that it's before transformation, and then image is obviously the one after transformation. So if they use those two terms, just keep in mind that that's what they mean. Now, so we know what function we start with, we know what function we finish with. We just have to figure out what transformations are happening, and hence figure out C and D. I think most people will see this question or see this notation, and they should be able to realize relatively easily that when you add C and D on the outside, that implies that we have translations. Now, the top one affects the X, the bottom one affects the Y. And when we just add C and D, that just implies that we move 1 unit to the right, or sorry, C units to the right, not 1, but we move C units to the right, and then we move D units up. So I just indicate that with the arrows. Okay. Now, there's a bit of confusion here because when you have the translations inside a function, it's not the same. So when we actually have this +1 here to the X, that's not a translation to the right. That's actually a translation to the left by 1 unit. And I think a lot of people get confused with that when relating that to the matrix notation. So this is 1 unit to the left because we're adding it, but then this one doesn't follow that rule for some reason. Like that's just the way that the numbers work out. This is actually 2 units down. Okay. And that's like a very common thing that we should know all the way back from when we learned turning point notation for quadratic equations. When we have y is equal to a to the power of x minus h squared plus k, we know that when we minus, this is actually positive h for the turning point. And this positive k doesn't make a difference. It's just positive k. So that's something that we know from a little while ago, and we have to kind of recall it here. So now, because of that, C is going to equal -1 because we want -1 there because we have a translation of 1 unit to the left. But then the D, it could just retain the sign. We just put D as -2 because we want -2 there because we have a translation of 2 units down. So in this question, I guess the best way of doing it would be to figure out what the transformations are first, and then from that determine the transformation matrix notation based on the form that they give in the question. Now, feel free to screenshot this, guys. This is just from the textbook. This is from the Cambridge textbook, the transformation section. I tell all my students that they should put this in their bound reference because this is a really good summary of all transformations. Obviously, you've got the actual transformation here. You've got the rules in terms of x dash and y dash. You've got your corresponding matrix, and then you've got what f of x looks like, or how the transformation affects f of x once it's actually applied. So feel free to screenshot this. It's a really good summary of transformations, and I would still use it to this day if I actually did methods still. But I would always use this, and I put this in my bound reference as well. And I actually used it in a bound reference, which is just as important. So I'll give you guys a couple of seconds to screenshot that, and then I'll move on to the next question. Also, if you have any questions, just feel free to pop it in the chat, and then we'll answer it from there. Cool. Okay. Now, part B, find the rule and domain of f inverse, or f -1, the inverse function of f. Now, calculator question, we could do this straight away on the calculator. What we do is I just copy my rule for f of x, and then I just swap x and y manually. That's probably the easiest way to do it. So I've got x is equal to 2 to the power of y plus 1 minus 2. Essentially, I just had y is equal to 2 to the power of x plus 1 minus 2, and I just swap the x and y. And then I could just say solve for y. So rearranging for y, I get this equation here. Now, this is y is equal to log, or ln. Now, ln, if you guys don't know, is equal to log base e. It's the same thing. Now, what I should recognize is that log base e of x plus 2 over log base e of 2, that actually combines. And that's an actual log law, yeah? Like when you have like a log divided by a log, you can combine them into one.
Yes.
Yeah. So there's actual log law for this that you can simplify. This actually just becomes f inverse of x is equal to log base 2 of x plus 2. Essentially what happens is that the bottom log, or the bottom number inside the log, becomes the new base, and the top number inside the bracket remains the same. Now, yeah, just check the textbook to actually confirm that.
Not a log law,
but like not a log law, but it's like but I'm pretty sure it's like part of the rules set for logs. Yeah, that's a really useful one. What you'd have to do is solve the equation by hand, and then you would get this directly. So yeah, just solve it by hand and you'd get that. I wouldn't leave it like this though, just because it's not fully simplified. I don't think that would get full marks. So that's why I would highly recommend putting it into this form here. Sweet. So that's the rule for f inverse of x. And you can see I've actually got no working out, which is completely fine. There's two indicators that there should be no working out for this question. The first one is that this question is only 2 marks. And if they're asking for 2 things, you can safely assume that you get 1 mark for each of those things. So 1 mark for the rule, hence there's no marks for working out, so there's no point putting it in, and then 1 rule for the domain. So that's why I just put the rule straight away in the calculator. I guess another indication that that you don't need any working out is because it is a calculator-based question. So there's no value in providing working out because you can just get the answer straight away in your calculator. So that's kind of like my rule of thumb. If you don't need to do any hand working out to actually solve it, just don't put any hand working out in. Just leave it blank. And just put your don't leave it blank. Put your final answer, but you don't need to show any working out. Now, with the domain, there's a couple of ways we can solve this. We could just figure out the domain of this graph like individually, just standalone. So what we can do is just graph it and then see what happens. So you could kind of see what's happening here, but it's kind of hard. We know logs have asymptotes, so it's hard to see what the asymptote value actually is. You could just see it from the graph. You can see it's -2 because we have a translation of 2 units to the left from our log. But the easiest way of doing it is because they've given the graph here, we recognize that this is f. So the range of f is the same as the domain of f inverse. So I just write domain of f inverse is equal to, I don't have to say range of f, but I can use that to work it out. So I can see the range of f is 2 to infinity. Round bracket 2, because we have an asymptote at y is equal to -2. So -2 to infinity. So that would be the same as the domain of f. So 2 different ways of solving that one. Either way will get you the correct answer. Pretty easy question so far. Find the area bound by the graphs of f and f inverse. It's really good that we've got a graph here because now we can draw what f inverse looks like on the same graph. So I got the asymptote at x is equal to -2. And then I just reflect this in the line y is equal to x. Doesn't have to be, I'll just rub out some of the stuff here. Doesn't have to be perfectly exact. However, we want it to be, roughly, so we can actually see how to calculate it. Because we know that when we calculate areas, it's really important that we get the regions of our graphs right. For example, we need to know where they intersect, and we also know when one graph is above the other. Because we should know that when we have the area between 2 graphs, the area is given by the integral of the top graph minus the bottom graph, dx. So to determine which one is above and which one is below, we need to graph it. So I've graphed the inverse function here. I'll just graph f of x as well. And we can see, well, we can't really see it, to be honest, but I'll just zoom in a bit. Now we've got this overlapping area here. It's very slim. However, we can still determine it. So to find the area bounded by 2 functions, what we need to do is, which would be xl for the lower bound, xu for the upper bound. And the easiest way of finding them is just solving one function equal to the other function. Well, that's one way of doing it. There's more than one way, but for working out, I'll just say f of x is equal to f inverse of x. What my students know as well is that f of x is equal to x, because a function and its inverse always intersect, or 99.9% of the time, intersect on the line y is equal to x. And you can see that this function does, because graphically, y is equal to x looks like this, and you can see that they perfectly correlate. Well, they would if the graphs were really good, but just believe me when I say a function's inverse always, or almost always, intersect on the line y is equal to x. So it's easier to solve this equation. So either way will get you the right answer. So let's just do that now. So I solve f of x is equal to x. And let's solve that with the calculator. And we get -1 and 0. And you can see that correlates to our graph. So we can see 1 is at the origin and the other one is to the left of the origin. So -1 and 0 makes sense as our x bounds. And if you guys don't believe me, I could change x to our inverse rule and I'd get the same answer. -1 and 0 as well. Sweet.
Would there be some scenarios where if you try to solve the function for the inverse, you wouldn't be able to do it and you have to rather use like the function of x, like when the inverse, you can't find the inverse easily?
Yeah. So Heshan just asked a question. I'm not sure if you guys heard him, but I'll just repeat it. Are there any other times where you don't know the rule for the inverse and you have to still find the intersections between a graph and its inverse? That's actually the case. There's been a couple of questions in the past where the inverse function is really hard to find, or it's like impossible to find just because of the equation that you're given, but you're still asked to find something to do with the inverse function. So in that case, you would just use this because you don't actually need to know the rule for the inverse to solve where they intersect. You just solve f of x is equal to x and you get the same solutions. So it's not only something that's more convenient, it's actually sometimes necessary to do.
Question, you said 99% of the time the inverse intersects at y equals x. So when does the inverse not intersect with y equals x?
Yeah, good question. So it's like, there's no actual rule. I actually did a bit of research into this because I was curious, because like it came up one time and I was really confused. There's actually no like given rule to say, oh, when it intersects with y equals x and when it doesn't. It's just purely based on the graph. I'll give you an example where it doesn't. Negative x cubed. I shouldn't do it on the calculator because I don't want to stuff up the working out, but I just draw it by hand. There's actually one situation where it intersects with y is equal to negative x. Yeah, the line y is equal to negative x. So the graph looks something like this. And then the inverse looks something like this. So this is negative x cubed, and this would be negative x to the power of 1/3, which is the inverse. And you can see that this actually intersects along the line y is equal to negative x. So if you have a graph, or like if you can determine a graph, then you should be able to determine, or you should be able to graphically see if it intersects along like the negative regions, or like negatively, or if it intersects along like the positive, like a positive slope. So if it intersects along the negative slope, it definitely intersects along the line y is equal to negative x instead. But this is like a rare case. I'm not sure exactly why this happens in this case. There's no rule for it. But most of the time you can assume it's on y is equal to x and just use a graph to determine that the intersections happen along like these regions here. Because if it's in these yellow regions, then you know it's in the line y is equal to x. If it's in the opposite regions, then you know it's in the line y is equal to negative x. Yeah, hopefully that makes sense. If you need more clarification, I'm happy to answer that a bit later once we've answered the rest of the questions. But just know it'll always be along the line y is equal to x or y is equal to negative x. And to determine which set of quadrants that it's in, just use a graph. Cool. So now that we know the intersections, we can find the area. And the most easiest way to find the area is just do your bounds, -1 to 0, of your top function minus the bottom function. So that's the general rule for finding the area between two graphs. So in this case, the top function is just talking about the function that's physically above the other one, or like vertically above. So in this case, it's the inverse function here, because we can see where the area is actually formed, the inverse function is above. And then I use a different color. The regular function is below. So in this case, I could just write f inverse of x minus f of x dx. And then putting this in the calculator, I would get my answer. Now, if I didn't know my inverse function, and that's definitely very possible, there's actually a way of finding the area again without knowing the inverse function. We use a bit of symmetry. I'm just going to redraw my region there. So this is my area here. And as I said before, the two functions are symmetrical about the line y is equal to x. Now, if that's the case, then what I can do is I can find the area bound by x and f of x, which is just that bottom half, and then I multiply it by 2, because that'll double my area. So then I get the other half, and then it adds up to my full area. So two different ways of finding the area. One, you don't need the inverse rule, but because we have the inverse rule, we can just use that one. But let's say if I didn't have it, I'll just rewrite it with a different equation. So or 2 multiplied by the same bounds, and then just x minus f of x, instead of f inverse of x minus f of x. So the only two changes is I use the function x as my upper bound, but then I multiplied by 2 to compensate for the fact that I'm only finding half the area. But again, we know the rule, so we can just do it on the calculator. It's not too bad. Let's do that now. So the integral from -1 to 0 of my inverse function. Now I could define my inverse function as a separate function, but for now I just copy paste it. But then for my function, I just write f of x dx. And I get this answer here. Again, no need to do any working out. Don't even have to write the integral. You could just write the final answer. So this is the expression. It doesn't say use decimal places, so assume that it means exact values. And then I write unit squared because I found an area. So unit squared is just the general unit for area. This question, you can see it's a few more marks. It's 3 marks. So probably one mark for finding the intersections along with the equation that you used, 1 mark for the expression for the area, so top minus bottom, and then 1 mark for the final answer. Sweet. Part D of the part of the graphs of f and f inverse are shown below. So it's good, just like similar to the graph that we had before, kind of confirms our theory about the inverse being on top. Find the gradient of f and the gradient of f inverse at x is equal to 0. Again, pretty easy question. The gradient of f would just be f dashed of 0, and I could just find the answer of that. So how to do it on the calculator is I do d dx of f of x, and so that's the derivative, and then I just substitute in x is equal to 0. So I just say given with that vertical line, and that just substitute in a value. So I get 2 log e of 2. Again, ln is log e. A common mistake that people make is that they think that they can put 0 in there instead of substituting on the outside. What actually happens is it evaluates f of 0 first, because it's like BODMAS, like it does the operation first, and then like it does the outside one then. So you actually evaluate f of 0 and then you differentiate that. F of 0 is a constant value because it's not variable anymore. And then you differentiate a constant value, you end up getting 0. So it's actually like a very common mistake that people make, and then they'll just put 0 as an answer. But what you should do is you should find the rule first and then substitute it on the outside, just to like, go around that mistake that people make. So it's 2 log e of 2 as the actual gradient. Sweet. And we do exactly the same thing for our inverse function. So I just like copy and paste the same line of working out. And then instead of f of x, I just put in my inverse. Sweet. Now, I was like asking Heshan before, how do I actually write this? So like, I just do f inverse of x, but then I wasn't sure where to put the dash, if I should put it like before or after the -1. I was like, because it looks weird. It looks like it's to the power of -11. So I'll just put d dx on the outside. Yeah. And then just say at x is equal to 0 is equal to 1 over 2 log e of 2. Sweet. I guess one thing that's interesting to note for these two gradients is that you can see there's a pretty close correlation between them. Just one is the reciprocal of the other. I think that's pretty interesting to note. And I'm pretty sure that's always the case for inverse functions. The gradient would just be the reciprocal of the other one. Not the inverse, but like the reciprocal. So you flip, you just flip the fraction, whatever it is. Cool. Now, got this new function here. The functions of gk, where k is an element of r plus, so introduces this parameter here to positive real value, are defined with domain r such that gk of x is equal to 2e to the power of kx minus 2. So this question introduces a new type of function, or a new function rule itself, and it's got a parameter here. Now, this subscript here doesn't actually mean anything mathematically. It's just saying that k is like changes the function, which is like, I guess it's pretty obvious, but the question just wants to emphasize that. So my presumption is if you put like a value in, like let's say we have g2 of x, that just means that k is equal to 2. Now, although like this notation might confuse a bit of people because it's not like an official, or like it's not like a standard notation that we see all the time. But just know that if you have a k in the general form, and then you replace that k in the subscript with some number, then that just replaces the k number in the expression. So for example, if it was g0 of x, then it'd be 2e to the power of 0 times x minus 2. And then just evaluate it from there. Sweet. Okay. Find the value of k such that gk of x is equal to f of x. So what it's essentially saying is that we want 2e to the power of kx minus 2 is equal to our function f of x, which was 2 to the power of x plus 1 minus 2. Now, you could do this by hand, but I'll just do it on the calculator. Now, I should really define my function as well. So I'll define my g of x. I'll just make a g of x. It's not worth making a g k of x. It doesn't really add much value. And it's just easier to write g of x than g of k. So new function here, just define it as g. And then what I'll do is I'll say g of x is equal to f of x, because that's what the question is stating. I'm just putting this equation straight into the calculator. Not much algebra involved. Now I want to solve for the variable k. So we'll see if this actually works, and it does. So we get k is equal to log e of 2. Sweet. I'll just write about all this other stuff. Kind of clear to see. Sweet. And this question's, I think it's our first 1 marker of this big question. 1 mark just means you literally just need the final answer. Like you don't even need any working out at all. Cool. By no working out, I mean like we wouldn't even need this, by the way, but I'll just include it just for your reference. Part F, find the rule for the inverse function gk inverse of gk. So, yep, again, we just take our rule for the g of x and just swap x and y. So I just write x is equal to 2e to the power of ky minus 2. Could do this by hand, but we're not going to, because this can be done in about 10 seconds. And we get this here. Why is it like this? Probably because, okay, so like now okay, so I've got a bit of a problem here. It's actually kind of good that it ran into this problem, but it wasn't actually intentional. I see that I've actually got no k in my expression. So that kind of confused me when I first saw it. Like, what's going on? Now, what's happened is that I actually have k defined as a variable from some previous working out that I did, like before this seminar. So pure mistake. What I do to clear it on my calculator is I click this cog in the top left, variable manager, and then it shows me all my variables here. And I can see I've got k defined as this value here, 61. It's kind of weird. I just tick it and then delete it. So that should fix that. And then if I solve it now, I get it in terms of k. So that's kind of fixed my mistake. But if that ever happens to you, where you get a weird answer that you don't expect, that's when you should question it and then go check your variables to see if k is still defined. How do you clear variables on the TI? I'm not sure how to do that.
I don't think there is a problem with them.
Okay, yeah. Okay, so TI shouldn't be an issue. I think it's mainly a CAS issue where you define your variable in some place, because it defines it on dynamic graphing. Maybe just check if it defines it on dynamic graphing on the TI. I think that was my issue. But let's continue anyway. So we got out of that issue. So I just write gk inverse of x is equal to that expression there. I'm going to rewrite it in native form. Don't lose any marks if you write it into that form there. But I'm just going to write it in a more readable form like that. And it doesn't ask for the domain, so no need to include that. I think one interesting thing to note here is that it asks for the rule of the inverse functions, not just the singular function. I won't give away the answer for that, but if someone like has a theory about why it asks for the inverse functions, feel free to leave it in the chat and you could just confirm. I'll just confirm whether you're right. But yeah, it asks for inverse functions. It's not a mistake. Why do people think that is? Just put that in the chat as I continue the next questions. G of I, describe the transformations that map the graph of G1 to the graph of GK. So as I said before, G of 1 is essentially G of K, but when K is equal to 1. So if I did that, G1 of X, that should equal 2e to the power of Kx, but when k is equal to 1. So just be 2e to the power of x minus 2. And then gk of x is equal to 2e to the power of kx minus 2. I think someone has an answer in the chat, because k is variable, so the function can change. Yes, that's very close. I think, so yes, k is a variable, and that's the reason why we have multiple functions, but it's because k can adopt multiple values that you actually have. I think the textbook calls it a family of functions when you have a parameter. So a family of functions means multiple functions. So whenever you have a parameter, k can adopt multiple values, which then produces multiple graphs. But yes, it's because k is variable, so that's good. Sweet. So I have g1 here and I have gk here. What's the transformation that goes from g of 1 to g of k? I mean, looking at the equations, we see the only difference is this k. Now, again, hopefully you guys remember transformations. It's one of those things that's kind of just, you get used to it as you do more practice. So whenever you multiply a value with the x, that's a dilation. So this one would be a dilation. Now, whenever we multiply the x, it's kind of counterintuitive. It's a dilation from the y-axis. And it's also by factor. This is like the most common mistake for this question. It's not by factor k. It's actually by factor 1 over k. Again, it's just because of the way the numbers work, that whenever you multiply a value with x, you have to find the reciprocal of it to find the actual dilation factor. And if we go up to the transformation screenshot that I had before, you can see that when we have a dilation by factor of a from the y-axis, you can see that we actually multiply our x value with 1 over a, or just divide x by a. So we actually don't multiply by that factor, we actually divide by it. So that's why I've written 1 over k instead of k. Sweet. So that's why that table is really useful, because you can use it for any type of transformation question, whether actually evaluating what a transformation is or determining what the rules are. I think that table is useful for both. So dilation by factor 1 over k. And it also gives you that, like, the transformation description as well. So I can just copy that word for word, and I can just replace the factor with whatever's appropriate to the question. I think that's also really valuable as well. But dilation by factor 1 over k from y-axis. I think all those, phrases in the sentence is really important. So dilation, obviously important to get the right transformation. By factor 1 over k, don't just say by 1 over k. Say the word factor, because it make it really clear. And then you have to say your axis as well. Even something like from, that's really important as well, because you're going away from the y-axis. You have to emphasize that as well. So that's something else to put. Sweet. Okay. So describe the transformation that maps the graph of G1 inverse onto the graph of GK inverse. So essentially exactly the same question as before, except in terms of the inverse functions. So what we could hypothetically do is find the rules for the inverse functions and do exactly the same process. But I'll tell you guys a shortcut here. Whenever you're going from an inverse to another inverse, the transformation is exactly the same, except you just swap your axes. The same way that the inverse functions just swap their axes, it just swaps x and y. Same thing with the transformation. So this transformation would be exactly the same. Everything will remain the same. So dilation by factor 1 over k, but instead of from y-axis, it's from x-axis. And that's not just a rule for dilation. It works for every single transformation there is. So you just swap the axes and it works out exactly the same. So maybe I'll write that on the side just so it's super clear for you guys. So inverse functions adopt the same, I'll just say T's for transformations, except the axes are swapped. i.e. x becomes y or y becomes x. Cool. Again, we could have done it the long way, but again, the long way takes longer and we want to save time. So that's why we do it this way. Any shortcut like that adds up. So I recommend, getting to know them if you can. Hopefully we've gone through a couple here, but if there's any more, just like write down like a list of them in your bound reference or something like that. Just keep like a reference sheet about any shortcuts that you know, because sometimes they're necessary to use. In this case, it just saves time. Cool. Okay. So part H, the lines L1 and L2 are the tangents at the origin. Just underline that because that's important, to the graphs of GK and GK inverse respectively. So GK just aligns with L1, GK inverse aligns with L2. Okay, just write them on the side. Find the value or the values of K for which the angle between L1 and L2 is 30 degrees. Okay, so it's kind of hard to know how to solve this without a graphical representation of what's going on. So what we should do is get a graphical representation of GK and GK inverse. Now, we know that it has a parameter, so it's pretty hard to sketch. What I'm going to do is I'm just going to sketch it for just a random value of K. This is purely just to get a graphical representation of it, but it's not actually used to solve it directly. So what I'll do is I'll just write 2e to the power of kx minus 2, but I'll just replace k with, I don't know, 1. That's fine. I get this graph here. And then if I do the same for the inverse, I just replace k with 1. Just get this here. Again, it's just to get a graphical representation of what's going on. Get both graphs on the screen, and I can see that this is what it looks like, roughly. Now, k will change how the graphs look, but again, it's just rough to see what happens. So I'm just going to, actually, I draw this in the working out box. So what's happening here? I'm just going to draw an axis. This here, this there. From the equations, we can kind of figure out that we have asymptotes at y is equal to -2 and x is equal to -2, like that. Now, we worked this out in the previous question, I'm pretty sure, but you could kind of double check this, that one of our intersections always happens at the origin. And you could work that out mathematically as well. But one of our intersections always happens at the origin. So regardless of what k value it is, the graph will always pass through there. And then hence, same as the inverse as well. But the graphs look something like that. So this would be GK, this would be GK inverse. Now, the tangents at the origin are the lines L1 and L2. So L1 corresponded to GK. As we can see there, also said in the question as well. So I'm just going to draw a rough line, tangent line there. So L1 is there, and then the other one is the tangent line of the other graph, which is like that. So L2. Now that we have a graphical representation, we can actually see what the question is talking about. It's pretty hard to see. It's pretty hard to determine that just from the words. What it's saying is that the angle between L1 and L2 is 30. That literally just means this angle there is 30 degrees. So we have to find the values of K to make those tangent lines have an angle between them of 30 degrees. So it's kind of weird. Like, a lot of people would probably read this question and think, oh, I don't know how to do it, and just skip it, which is fair enough. Like, it's not an easy question. That's what I start off with. It's a pretty difficult question. I know, like, probably less than 5% of people got full marks for it. And like a very small margin of people got 1 mark for it. So yeah, it's like, on average, it's a pretty hard question. But we're here to answer the easy questions and the hard questions and answer them well. So that's what we're here to do. That's what we'll strive for. So we have to think about and kind of break down this question with as much information and knowledge as we have. Okay. Now, my first instinct for this question is, okay, I know the angle between my tangent lines. So this is kind of what's going on. So I'm just going to redraw this without the other lines because they're not that vital for this question. So I've got L1, L2, and my angle here is 30 degrees. And I also have a y-axis and an x-axis. Now, this is something like this is a basic idea that we should recall from maybe year 9 or year 10. I forgot when, but the angle that something makes with the x-axis is equal to tan inverse of the gradient. Or you might know it in the other form that says the gradient is equal to tan theta, where theta is the angle that the line makes with the x-axis. So I can use that principle here. I can say that theta inverse is equal to tan inverse of the gradient of L1, which is that line there. And did I figure that out before? No, I didn't actually. So what I can do is I can figure out my gradient of L1 and I just evaluate that on the side. So I say M of L1 is equal to, and then I just evaluate that on the calculator. So GK is, actually I know GK, or GX, I've already defined it. Find the derivative of G of X and then substitute in X is equal to 0 because our tangent line is at the origin. And I can see that this has a gradient of 2K. Now, M of L2 will just be 1 over 2K, because I said that before. An inverse function and a normal function have reciprocal gradients. So that means that theta 1 is equal to tan inverse of 2K, because that's M of L1. And then theta 2 is equal to tan inverse of 1 over 2K. So they're my two angles there. So this is one way of solving it, and then finding the difference between these angles, and it's equal to 30. Now, I actually tried this way before, and it didn't work, unfortunately. So we have to think about, I had to think about another way of solving it. Now, another thing that we know, like, it's not only that the angle between them is 30 degrees, it's also important to note that we're talking about a graph and its inverse. So this has come up in a couple of questions before, so you can see that we're trying to hammer this home. It's that a graph and an inverse function have like a lot of symmetrical properties. And one of them that keeps on coming up is that it's symmetrical about the line y is equal to x. Now, what's that got to do with this question? It means that this angle here is 30 degrees and this angle here is 30 degrees because the L1, L2 split along the diagonal there. So it splits along here, which means that this angle has to be the same as this angle. And because between the axes we have a right angle, they just split up into like 30, 30, 30 in each of those little segments there. And that actually makes it really easy for us to solve, because instead of finding the difference between like these two complex expressions, which I couldn't even solve for my calculator, what I can just say is that this angle here for my gradient should be equal to 30 degrees. So instead of solving the difference, I just say, okay, theta 2, which is tan inverse of 1 over 2K, that's just the angle that's between the line and the x-axis. I just say that tan inverse of 1 over 2K should be equal to 30 degrees. And then that'll give me a K value. So again, the angle between the tangent lines is equal to 30 degrees, but because we have symmetry, because of the inverse functions, that means this angle here should be 30 degrees and this angle here should also be 30 degrees. Now, it's a coincidence that it's 30 degrees, like they're all 30. Like, let's say if I had, let's just do it, like change the question a bit just to show this. Let's say if this was 40 degrees in the middle, does that mean that the other ones would be 40 degrees? Well, actually no, because we have a right angle. So that just means that this angle should equal this angle here. So if the middle is 40 and it adds up to 90, then we have 40 plus 50 is equal to 90. So this will be 25 degrees. This will be 25 degrees because our XY axes, the quadrant, should add up to a right angle. So in that case, it would be different, but it's pure coincidence in this question that it's equal to 30 degrees. So that splits up into 30, 30, 30 for 3 parts. Is that clear? Yeah. So it'd be 30, 30, 30. Again, any questions, leave it in the chat. This one's like a pretty complex question and like a lot to break down. But let's just go ahead and evaluate this. So we can see that graphically, we're just trying to solve this tan inverse of 1 over 2K is equal to 30 degrees. And I just solve for K. You can do this by hand, but again, let's do it on the calculator. We get root 3 over 2. Cool. Now, that's one solution. We can actually solve the other one equal to 30 degrees. Just going to get rid of these things here. Now, this graphical representation shows that L1 is above L2. Now, that's actually not always the case. I guess if I just write down the gradients of each of them respectively, the gradient of this one is 2K, and the gradient of this one is 1 over 2K. But what if K was like a smaller number, a number like less than, let's just say like K was equal to 0.1. then we would actually have it the other way around where L2 is above because we're dividing by a smaller number. Yep, so my calculator is in degrees, though represented by the deg there. And this question's important to have it in degrees because the angle in between them is 30 degrees. So I put 30 in there. But like, let's say it said the angle is equal to pi on 6 instead, then I'll put it into radians mode. Cool. Anyway, as I was saying before, L2 doesn't necessarily have to be below L1. It depends on the K value. So I should solve L1, like this angle here, to be 30 degrees as well, because we could easily just have it like this is L1 and this is L2. It just depends on the K value. So we have to cover both cases. And that's why the question says that values of K, because it's not only one. So I also have to solve tan inverse of 2K is equal to 30 degrees as well. And that'll give me another K value. And I get √3/6 for this one. So I get those 2K values there. Again, this is my approach. It's not only one approach to it. There are other ways that we're talking about before the seminar about if you do SPECH, then there's some sort of shortcut or like some alternative method. It doesn't really matter. Again, as long as everyone has like a different, I guess, knowledge base and different methods that they're used to. So just stick to whatever you're used to and try and figure out if, try and see if like you would be able to solve this and give it a go independently as well and see if you can like derive everything that we derived here. And if so, then you're on the right track and you're doing a really good job. And if not, then you might have some alternative approach, which might be better. You never know. Cool. Okay. So these are the 2K values to get you the angle between them as 30 degrees. And I guess we could double check it as well, just by substituting in, these K values, seeing what the angles are. But I think we solved it pretty well, so it should be okay. Now, part I, let P be the value of K, for which K or GK of X equals GK inverse of X has only one solution. Okay, and then it asks to find the value of P. Now, I'm not sure why this question introduces a new variable. I think it's just to confuse people, but it's just saying P is the value of K to get one solution. That's all that's saying. I think normal questions would word this as find the value of K to give you one solution to this equation, but this introduces a new value P, which makes this question pretty confusing. But don't worry, it's exactly the same thing. Now, I guess from like, I'm just thinking like when I was in VCE 3-4 methods, whenever I saw a question where it told me, okay, find the value of K for one solution, find the value of K for two solutions, find the value of K for no solutions, the first thing that comes to mind is determinant. I think that's like pretty much everyone's instinct. Number of solutions equals determinant. Now, one thing they actually don't say explicitly, it might be implied, but it's not very explicit in the course, is that the determinant only works for quadratic equations. Now that's implied from the form or how you get the determinant. It's b squared minus 4ac, where the a, b, and c are the coefficients of your quadratic equation. But again, it's not very clear. So when I was going into methods, like when I was progressing through methods, one solution, how come it doesn't work? It's like an easy way to just check if it works or not is just to see if you've got a quadratic equation. Now, for this question, we don't have a quadratic equation. We have an exponential equal to a log. So that's that function there, and there's inverse. Exponential log, you're not going to get a determinant from that equation. So we need another method to solve it. Now, again, I would be stuck if I was up to this point. I don't know how to solve one solution. It's kind of weird. So what I want to see is, or what I want to do is I want to see what's happening graphically, because I want to see how K, or the value of K, affects my two graphs. Now, what I can do is I can sketch my two functions and, like put in different K values manually. But on the calculator, there's a really easy way of doing this. So what we do is on this calculator, you go graph and tab, this thing here. And I've already got my functions here. I've got my GK here and my GK inverse here. And then what I can do is I don't press the normal graph button. I press this, this secondary parabola, like this one with like multiple dotted lines here. Now what this does is, well, it's called dynamic graphing. Essentially, when I have a parameter in my equation, that's why K was 61 before, by the way, because I was doing this here. But what's happening is that I can change the value of K, and then that changes like with this slider here, and then that changes what the graphs look like. It regraphs it for that value of K. Now, so again, I type in my equation with my parameter. In this case, it's 2 equations, and I select the second button here, and that'll automatically produce this slider. And then I can change the value of K with this slider, and that'll produce a different graph. Now on the TI, I think you sketch the graph, you write the rule of the graph first, and then you do go like settings and then add slider or something. I think so.
No, I'm just going to yeah, so on the TI,
yeah, cool. So a very similar process. It's probably just like a different tab. But yeah, you just add the slider, and then same thing as the TI. This part's the same. You could change the settings of the slider. So I could change the current value, which is just the current value that it's on. I can change the minimum and the maximum, and also the step size. So what I'll do is I just change it from -5 to 5, just arbitrarily. What I want to do is the reason why I've chosen a negative and a positive number is because I want to kind of encapsulate, like the negative and positive range, because I have no idea where, before starting this question, what value of K one solution lies on. So I kind of want to test it and then shrink down my range. Now, I've actually defined it as negative, and then I've realized that this question says that K is equal to R plus. So it's like, whoops. Sorry. K is equal to R plus. So it actually can't be negative. So I might as well just change my slider, because it kind of defeats the point of the question, to make it start from 1, and I'll go to 5. Again, purely arbitrary. Let's see what happens. I've already have 2 intersections here, and then when I increase it, I've still got 2. The reason why this cuts off is because it's asymptotic, so the graph doesn't have that good resolution, but will continue down there. So K equals 3, 4, 5, that still has the intersection down. Again, it just cuts off because the asymptote is getting too close to the asymptote. So the graph the calculator can't handle it. But you can see it's still got 1 intersection. So let's try and reduce it. I can see that the graphs are getting further away from each other. Like these graphs are kind of close to each other. Yeah, so like when you increase the value of K, it's getting further and further away. It's like stretching out. When I reduce my value of K, this is purely just from visualizing the graph. I see that my graphs are getting further and further away from each other. So what I'm thinking is that maybe I have to go less than 1, which is fine. It doesn't say anywhere that the K value has to be a whole number. It says it has to be a real number. So I guess let's make the minimum 0.1 and make the maximum and also make the minimum 0.1, make the maximum 1, and then a step size of 0.1. So this will iterate from 0.1 to 10. Cool. So I actually see that this version of the graph, I have value of 0.1. So that's cool. So with 0.1, I've got 1 intersection, which is good. Increase it. I have 0.2. Let's actually just zoom out. I've actually got another intersection there. Okay, so that's kind of stuffed it. But between 0.1, 0.2, 0.3, cool. Okay. So I've got 2 intersections here. I increase it. I'm getting further and further away. 0.4, it looks like 1 intersection. It looks like it's getting closer. 0.5, it looks like it's getting closer again to 1 intersection, but I'm not sure what's happening in the middle. So I just zoom in. 0.5, it looks like 1, but it's hard to tell. 0.4, you can kind of see the blue line at the bottom. Can you see it on your screen? Yeah. I see the blue line at the bottom. So it does overlap a bit. It's probably worth zooming in a bit more. Yeah, so you can see a gap there. So tiny gap, really small sliver, but you can see it still has 2 intersections, 1 at 0 and 1 roughly at 1. 0.5, it looks pretty good. I can't see any gaps. 0.6, I feel like, yeah, I can see the blue line a bit there again. So yeah, so 0.5 looks like critical value. But it's hard to determine. So let's say if I didn't know how to solve it by hand, then I would just write P as a half, as a pure guess, just from the graph. Like, is that pretty fair?
Yeah.
Like in the situation where you can't do anything else, just put P a half same as 0.5. Put P as a half. And yeah, if you get it right, you get 1 mark probably. You would get mild mark because if it's right, if it's wrong, you lose nothing. So might as well just take a guess. Now, if we wanted to solve it actually, then what we'd want to do is recognize that a graph and its inverse have that property where we have symmetricality about y is equal to x. So you can see in like 3 or 4 of these questions, the inverse function properties have really come into play, where it's not very emphasized in the course, but it's actually really important to solve these questions. Now, for one intersection, you can't really see this from the graph, but I'll just tell you guys that if you have a graph and its inverse function and they intersect along the line, or like you only want them to intersect once. So let's say one's like, I'll draw the graph a bit better than that. One's like this and one's like that. Then what happens at that one intersection point is that you actually have the same gradient. So the same gradient passes through there and you essentially have the same tangent line. So I just say L1 is equal to L2, just recycling my notation from before. So if the gradients are the same, or like the same tangent lines, you essentially just have the same gradients at that intersection. And we know that the graphs intersect at 0. You can see it in all these different K values. There was always one intersection at 0. So that is obviously the one that we want to keep. So what I say is that the gradients are the same, and we could just use the same gradients from the previous question because we already found them. So we found the gradient of 1 was, where did I write it? There, 2K, and the other one was 1 over 2K. So we get 2K is equal to 1 over 2K. Essentially just M1 is equal to M2 at my intersection. Or I can just say, actually, do you know what? I'll say not at the intersection, I'll just say at tangent. Cool. So I get 2K is equal to 1 over 2K. And then I can solve this by hand. Let's do it by hand because it's pretty easy. 4K squared is equal to 1. K squared is equal to 1 quarter. Therefore, P is equal to the square root of 1 quarter, which is equal to 1/2. Square root, you could get plus or minus, but in this case, it's because K should be greater than 0. And that's how I solve that question. So you could take 2 approaches. You could do the graphical approach like I did here to get the answer, but then you don't get any working out marks. This is working out plus it gets you the final answer as well. So kind of a combination of both is good because once we get an answer, then we can use our graphs to kind of confirm if our hypothesis is true. Yeah.
I just realized that before my audio settings were wrong, so none of you could hear me. Yeah, but if you want to add a slider to your TI, that's what I was saying before. All you have to do is just type it in, just a function with K in this case, and then you can go to your menu and then go actions and then insert slider, and then that'll get you the slider just like how Adrian has it on his screen on the CAS. Another thing is when you do this, especially on the CAS, I know for a fact it's on the CAS, when you define your value of K like this, if you go back to your main menu and you type in an equation with K, what's going to happen is it's going to remember that value of K just from that, from the slider that you had it before. And you have to actually go to your variable manager and delete your value of K, just like Adrian did at the start of the video. So that's probably why he even had that, in the first place, like defined as a variable. So just be careful with that, because if you use K again in an equation or a formula, you might get something wrong because it's defined as what you had before in the slider.
Yeah. So you can see I've typed like 2K plus 1 here, and it's actually evaluated as a constant, and that's because it's retained my value from the slider. Wait, did you say that's the same as the TI, or it's not?
I'm not sure.
Yeah. Okay. Yeah, I mean, it could be, like most likely is because the functionality of the calculator is pretty similar.
Yeah.
So 2K plus 1 here, and it's actually evaluated to a constant, and that's because the slider has saved my variable. So that's one downside of using the slider. I'd say it's like 99% good, but then there's just the one problem where it does keep your variable value. So you just have to manually delete it. And then that should be fine now. So if I type 2K plus 1 here, it keeps says 2K plus 1 after I clear it. Sweet. So this question, P equal to 1/2. One more question, just 1 mark. 1 mark question, but I feel like, yeah, like I think I read the exam report before. It was like 2% of people got the mark or something like really small. But okay, it's kind of weird notation for this question. We're going to dissect it a bit. Let A of K be the area bounded by the graphs of GK and GK inverse for all K is greater than P. Okay, so there's a couple of things to dissect in that question. We've got this A of K here. A of K is purely just saying the area. Now, the reason why it's A of K and not just capital A is because it's kind of treating it as a function of K, and that's because the area does change with the K value. So if GX looks like this, sorry, GK of X looks like this, and then GK inverse looks like that, and the area is just bound by there, and then presumably the K value changes the area. And that's pretty obvious to see. We did do graphing tab before, and we saw that the area does change. Like you can see the area is obviously widening up as we increase our K value. And that's actually a really important observation to make right here. I'll just change my values to make them a bit bigger scale. I can see that when I increase my K value, my area is getting like wider. So I can see that there. So increase the K value, and then when I decrease it, the area gets smaller. Now, the reason why I'm saying K is greater than P is because at the P value, I only had one intersection. So there's no value of doing, like, let's say K is equal to P, because you don't have any area anymore, because you don't have a bounded area, because you only have one intersection. So there's no point doing K is equal to P. And again, there's no point doing K is less than P because, K is less than P because like, that's not what the question's suggesting. This area is much easier to maintain. You saw that when K was less than P, you had some random area on the other side of the axis. So this kind of just keeps it, consistent. K is greater than P. You've got two solutions and they're in the same like region. Cool. Okay. So state the smallest value of B such that A of K is less than B. Yeah, that's just really weird. That's a really weird way of saying it. Okay, like if I read this for the first time, I would have no clue again. You can see that's a really common trend with this exam question. Ridiculously hard, but also the notation and the way that they word the question is like tricky on purpose. Like it's meant to trip up students. But let's try and like just dissect it and see what the question's actually saying. State the smallest value of B. Okay, so smallest value of B. Okay, such that A of K, the area, is less than B. So what the question is implying is that A of K has some limit, and then B is greater than that limit. But it's saying find the smallest value of B. So like, let's say if A of K, like the limit of that, like let's say like it approached 100, right? And what it's saying is that there's infinitely many values that B can adopt. For example, B could be 200, right? And technically, A of K is less than B is still true because 200 is greater than 100. But it's saying find the smallest value of B. So in this case, when A of K approached 100, you would say, no, B is not 200, it's 100, because that's the smallest value that A of K approaches. You could have 101, you could have 200, you could have 1,000,000, and they all work. But B is equal to 100 is the smallest value because A of K, or the area, approaches an area of 100. Does that make sense?
Yeah.
Okay, hopefully you guys get it. Again, if you like one more clarification, just put it in the chat. But what it's saying is that find the value of B, or find the smallest value of B such that that expression is true. What it's pretty much saying is that the area approaches the value, find that value. Like the area has a maximal value and just find that area, if that makes sense. To find the largest area that it has, so find the area that, find the value of the area that these graphs approach. Let's get rid of this. Now, again, a couple of approaches. What I would do is, again, what I did before, set up my graph and see what happens when I change the value of K, and I can see that my area is widening. So presumably what happens is that you can see that this trend happens when you guys probably came across this for your investigation tasks. You had to change around parameters and see how your graph changed. Now, what I saw was that when my value was positive, which is fine for this question, and when it increased, my area increased, so my graphs got further away. So like to confirm that hypothesis, what I'll do is I'll increase my values even more. I'll just say 1 to 100 or something like that. And I'll make my step size a bit bigger. I'll make it 5, just so I can get more extreme values. So K equals 1, K equals 6, K equals 11. And yeah, you can see the graph, like the graphs are getting further and further away, but it's kind of slowing down as we increase it heaps. Let's box in at the area here. This is my area now. Like you can see the graphs kind of cut off there. It kind of stops, but it's because, yeah, I'm going super vertical. So you can't, it doesn't really capture that, that behavior. Yeah, so like the graph should be vertical there. And we should just know that from log theory that like you're going to have an asymptote there. But because my K value is so large, it's getting super, super vertical here. And you can see my area is approaching this like region, like this little block region here. Essentially what's happening is that, okay, let's just draw like an undilated version. It kind of looks like, oh, wrong side of the axis actually. I'm just going to redraw this thing here without like the graph cutting off. What's happening is that this is the original version without dilation. And then what's happening now, I use a different color, use this color here, that the graph looks like this now after dilation. So my area, oh, like my graphs came from this to this, and then that to that. So it's actually stretching out, but you can see the box is bounded by this, or like this area is bounded by this box here that goes from -2 to 0 and -2 to 0 up there. So the area, -2, -2, the area of K is approaching a 2 by 2 square. Now 2 by 2 square has an area of 4. So as K increases, hypothetically from this graph, my area approaches 4, therefore B is equal to 4. And that would be one way of solving this question. Now, I'm not really a fan of this way, to be honest, but I know it's the most intuitive because I can see from the graph. So I might get this question, but I'm not really like, I don't know. I would say it's pretty, a more mature me would say it's a pretty good way of solving it. But if I was a student, I would say, okay, this is not like this is kind of like, I don't know, not the best way of solving it because it's not very definite. We're kind of basing it off a graph, what we see from a graph, which is, to be honest, it's a good way. It's not the best way in my opinion. So one way that I would try and overcome this is I would go to the main screen, and first I would figure out, I would literally just get an expression for the area between my function and its inverse. And then I'd find like the area as K increases, essentially. Now, what I can see from, it's really important to get a graph though, because what I can actually see from the graph is that, let's just decrease the value of K so I can actually see my graph better. As K increased, just imagine this graph extends down. It's just because the graphing calculator is bad. But imagine this graph extends down. My intersection gets closer and closer to -2. So like this graph extends down, you can see it's pretty close to -2. I won't get to -2 because that's the asymptote, but you can imagine that if this graph goes more and more, it gets more and more dilated, the intersection gets closer to that asymptote there. And one intersection is always at 0. So essentially my bounds of what's called bounds of integration are like -2 to 0 as K increases. So what I'll do is I'll evaluate my area as an integral from -2 to 0. And then I'll do like the graph minus the other one, like the top minus bottom, like I did before. So this is my inverse here. And then I'll minus my original function, which is here. Yeah, dx. And then maybe I'll get an expression for it. I probably won't because it's pretty messy. Okay. Oh, well, I do because I still have a value of K that I need to delete. Let's see if I get an expression. Okay, I do get an expression, which is interesting. So what I'll do is I'll substitute like different values of K and I'll see what happens. So like K equals 1, I get this here. Let's put it into decimal so it's actually readable. K equals 1, I get -7.
Maybe you're one minus top. Oh, negative because you're doing it on the correct.
No, that doesn't make a difference. I'm just doing the other way around. I just got to take the negative of it because I did the other way around. I did bottom minus top.
Oh, yeah.
Yeah, so K is equal to 3. I get that. K is equal to 4. Actually, no, I think I just got my expression wrong. I think this is just wrong. Yeah, I think I just typed my equation wrong. But what I'm essentially doing is I'm finding an expression for the area in terms of K. And then what I'll do is I'll do the limit as k approaches infinity. So if I do like k is equal like, I'm getting really close to it. But the reason why I'm getting like the other direction is because like my expression's wrong for some reason. I'm not actually sure why it's wrong, to be honest, but -2 to 0. I'm not sure, but there's something wrong with this equation here. I think I just copied the wrong thing. This is why you got to define your functions, because I didn't put it into brackets. Yeah. I was like, what's happening? Okay, let's do this again. Okay, so this is my correct expression now, I believe. So this is actually should be positive. Yeah, so what happened was I just minused my function, but I didn't minus the whole thing. I didn't put it into brackets. So like I wasn't carrying this negative when I was minusing it. Pretty rookie mistake, but yeah, anyway. So k is equal to 1, get a certain value. K is equal to 4, I get a certain value. K is equal to 10, I get a certain value. And you can see my values increasing. K is equal to 100, 3.96. K is equal to 1,000, 3.996. And you can see a trend here. She's getting super, super close to 4. And just to confirm that it gets super, super close to 4, what I said, this makes more sense now, it works. What I'll do is I'll do the limit as k approaches infinity. And I get 4. So that's kind of more mathematical approach. I'm getting a general expression for my area. I'm just doing the limit as k approaches infinity. And to get 4 there, it's like really nice feeling because you kind of know that you got it right. Because if you got b equals 4 from the graph and you get it algebraically as well, then it's kind of like a double check that you got it right. Cool. So yeah, like this question, yeah, you can see it's like a bit messy, but only 1 mark. You can take any approach you like. No working out. So there's more algebraic approach, a more graphical approach. I think a graphical approach is pretty good, but I would like to confirm my theories from the graph from like with algebra. So like, that's why I wanted to do this way as well. But yeah, I'd say like, what would you say? This is like the hardest question. Like this is one of the hardest questions that like I've ever come across. And it was on my exam, unfortunately. Like that's just unfortunate for me, but it's good practice for you guys. Overall, like it's a long question. And like we've been here for like an hour a bit doing the question, but obviously when I'm not explaining it and you're just doing it independently, then you would save a lot of time. But I think there's a couple of things to note for this question. First of all, you've got a good mix of like different topics into the same question. So you've got a lot of transformations, you've got a lot of, so a lot of inverse functions, which is like very possible for your SAC or for your exams, and a lot of like integration basics as well, but just applied to more complex problems. So I think, yeah, like what do you have to say about this question?
Yeah, also like a lot of those questions, like part I, part H, like the ones that are at the very bottom of these questions, they're designed to make students like fail and only have like 20% or even like 5%, some cases 2% of students in the whole state answering them correctly. Like that very bottom question that we just did where we found that area approaches a box, that's probably something that only like 5% of students or even less.
No, I reckon it's less.
Yeah, it would actually answer that correctly. So don't worry and that's actually what separates students that are getting like low 40s to like raw 50s, right? So that's how they separate it out. So don't worry if you don't know how to do them or if you find it challenging. The more you do things like this, the better you'll get at understanding how to do questions and understanding tricks. And just like how Adrian said, doing like a dynamic graph and trying to see how the area approaches a box and trying to figure it out that way, as opposed to doing it like a mathematical way. Like you'll understand different ways of doing different questions, the more exams that you actually do in the long term.
Yeah, I think Heshan said something in there like that they said pretty quickly, but it's like really good to note that these questions are not designed for like the average person. These questions are designed for like people, like they're designed to separate people from getting like 40 to 45 and 45 to 50.
Yeah, exactly.
Like, so these questions like for the upper end of the spectrum, and you notice that some of the questions at the start are super easy. Like that's on purpose. Like you're meant to get questions that cater for everyone, and then you're meant to get questions that cater for like the, like the upper echelon, or like a certain percentile of people. Like these questions are designed very strategically to like cover that range. So what we're trying to do is like obviously like your goal and our goal as tutors is to try and get you from like try and maximize the amount of questions that you can break into and get marks for.
Yeah, exactly.
Because that's what separates you.
Yeah.
Like you might notice that these questions, like, yeah, like they're not, some people might make mistakes. Fair enough. Like, we all make mistakes, but then like on average, like people should be able to answer these really pretty easily on average. but then as you get harder, as you get lower, it gets a bit harder, it gets a bit harder. Like this one's just subbing values into the grading function. Like this is purely done on the calculator. This question will be classified as pretty easy. But then as you go further down, the questions get more difficult and difficult. So what we do as tutors is we want to get you from a question like this to break into like a question like this.
Yeah, exactly.
And that's what you should be aiming for as students as well. Like think about questions as like challenge, like think about a question as a game. And you're trying to just like break into as many levels as possible. That's the goal of like a question. Like, and if you want to think about it as a game, like if you want to think about it as a sport, whatever you want to, whatever makes you like, I not enjoy it better, but whatever makes it more relatable as like something that you trying to strive to get further and further. And every question that you do, like every practice exam, you're trying to push yourself further and further. And like, that's what you should be doing as like students. And as tutors, that's what we, try and motivate our students to do as well. Like push further, like reflect on their working out. And what's it called? Cognitive metacognition, like thinking about your thinking, like thinking about what your process was and how can we refine that. So that's kind of like what we try to do alongside, our students as well.
Yeah. And it's about understanding like the different ways that you can approach a question as well.
Yeah.
There's always going to be easier questions. There's always going to be harder questions on the exam. So the more you do, the better in the long term. If you guys enjoyed this and you thought this was good and you enjoyed Adrian's teaching and how, if you do more of these exams weekly or on like a monthly basis, the more you do, the better you get. The more you can break into those harder and harder types of questions. If you like the way that Adrian broke down these questions, we actually do this quite regularly. We've done masterclasses for like differentiation, functions and relations, all those topics that you had at the start of the year. Yeah, they're on YouTube as well. Yeah.
But like we'll continue to do them like throughout like the lead up to exams as well. Like
exactly.
We'll do like more of these type of questions, but more for like, this is more integration focused, just a singular question, but we'll probably transition to more like exam like oriented questions, which cover like a wider range of topics and a wider range of other things.
Yeah, I think even probability.
Yeah. I just wanted to thank my students for coming as well.
Yeah.
Thanks for making time out of your day on Saturday to come. Appreciate it.
Yeah.
For the other people who like aren't our students.
Yeah, for the other people that aren't our students, if you guys want to join, it's really valuable. You guys get seminars every month according to different like topics in the textbook. Yeah, click that.
Yeah.
And also you get weekly classes. So the weekly classes is just like a Zoom group sessions that you get every single week. That's just covering like the theory and content. And then during the master classes, we go more into depth in like, obviously today we went into like a VCA question. So we'll go into more depth with regards to like VCA questions and how to break those down. You also get booklets, which have been designed with like easy questions and hard questions, again, mailed out to your house. And also for every single questions in those booklets, we have a website that breaks down every single one of those questions. So if Adrian just showed them the website. So we have this website here, which has like every single topic for every single chapter in our book. And if you click on one of them, then you can go into that and you have sets of notation. You have videos for every single one of those questions. So these are corresponding to the questions in our book. You can watch them. So this is just everything that our current students are getting as part of just like this masterclass seminar group session package that all our students are getting. So if you guys want to join that, I think it'll be really helpful, especially towards the end of the year as it's getting harder and harder. And you guys have to remember everything as well as learn new things and also focus on learning how to answer exam questions, because writing exam is also another skill you have to develop on top of learning the content.
I think like an important thing to know is that it's probably like pretty hard to like commit to like a new tutor, like especially like a private one. So like this is like kind of not a compromise in the middle, but it's like a best of both worlds. Like you don't have to like commit to like schedule time with like a tutor every week. Like you could do things autonomously.
Exactly.
So you also get like messaging, like you also get access to like messaging for help. Like you can message us for help at pretty much any time. And we'll just like reply by the end of the day with some like working out. So that's like, you get access to us all the time as well. And then also, as Heshan said, the paper revision and resources as well. I think like what we're going to do for today, like that special offer.
Yes.
So if you guys like sign up today, then what we'll do is we'll mail out like a year-long worth of questions. That will aid like with your practice revision. So
Yeah,
it's like
so-
similar.
yeah.
It's like similar to like Beaker checkpoints.
Yeah, exactly. Yeah.
So like, but better. And like
Functions and relations,
yeah.
like differentiation, all
Yeah.
that stuff. And then also you get access to the website, which has like video breakdowns of me and Adrian going through each one of those questions, exactly how Adrian teaches, exactly how I teach. So you guys can go through that autonomously just by yourself in between classes, and then you can continue onwards. So it's sort of like a revision for everything you've done, plus a continuation of like probability and integration and like good exam skills that you will learn and master over the next coming months. Yeah, so if you guys are interested in that, so we're only going to have that open for like today. So if you guys are interested in that, you can just head over to our website and you can purchase that through the link. Maybe put the link in the Zoom as well.
Oh, yeah, so, yeah.
Yeah, so you can buy it through this link. We're